These questions were asked in quiz format as one of the assignments. First question, and these were randomly chosen, so yours might look a little bit different. This term appears in one of the Navier-Stokes or continuity equations. Pick the best description of where this term fits. Now, looking at this term, things about it, it's a partial derivative. It's with respect to time. And that's a y velocity. So this is a rate of change with time of the y velocity. That's an acceleration. It's a temporal acceleration. It's not because the particle's moving to somewhere else in space. And it's to do with velocity in the y direction. So let's look at the options. Spatial acceleration term, no, it's not spatial. Unsteady term in the continuity equation? Well, our continuity equation is steady, and even the unsteady continuity equation doesn't have a term like this in it, so that's not it. Viscous stress term. The viscous stress terms are all second derivatives, so that's not it. By elimination, I sure hope it's this one. Temporal acceleration, so that's acceleration with time. In the y momentum equation, that's a y velocity. So that's the right answer. Question 2 again says, this term appears in one of the Navier-Stokes or continuity equations. Pick the best description of where this term fits. And this time it's got a velocity, that's a y velocity. It's got the x velocity on top, and it's direction y on the bottom. So this is about the velocity gradient of the x component of velocity and how much it changes as we go in the positive y direction. So that's u at two different locations in y. So in this instance, di u di y is negative. As y increases, u is getting smaller. And that has to do with acceleration due to a particle moving from here up to here. So di u di y, if there is a non-zero di u di y, then as a particle moves upwards because of this y velocity v, it's going to experience an acceleration. So this is an acceleration due to the particle's motion in space. And it's an acceleration, it's a change in the x velocity, so it's the x momentum equation. So let's check this out. Acceleration in the x direction, that's right, due to movement in the y direction. So, bingo. It's not a viscous stress term. It's x momentum transport in and out through control volume surfaces facing in the y direction. X momentum, yeah, it's about acceleration or about momentum. If we looked at a box, then the stuff coming out the top is going slower than the stuff that came in the bottom in the x direction. So that's an equally good answer. Y momentum transport? Definitely not. So either one of those answers were good answers. Question 3. What does this equation represent? Well, let's look at it. It's a Navier-Stokes equation. It's got acceleration terms on this side and force per unit mass terms on that side. So that's acceleration equal to force per unit mass. So, conservation of mass? Nope. Conservation of momentum in the z direction. Well, it's z momentum because it's got a z velocity component, that's w. All of these w's are about how the z velocity changes. It's incompressible because that's something that we assumed when we derived this equation. And it's about momentum, that's F equals ma kind of stuff. So I'd say that's a good answer. Steady incompressible conservation of linear momentum in the z direction. Well, we said we were going to use steady flow just about all the time in this course. And you could certainly use this equation for steady flow, but it doesn't represent steady flow until you cross out that term and say it's zero. So it's not steady. And conservation of angular momentum. Well, angular momentum is just linear momentum, but expressed in a different coordinate system. But this only deals with one component of the linear momentum. So you'd need all three components of the linear momentum to represent the angular momentum. So that's not a good answer either. So incompressible conservation of momentum in the z direction. It's a Navier-Stokes equation. Question 4. This equation has 9 terms, 4 on the left side and 5 on the right side, so that gz is term number 6. 1, 2, 3, 4, 5, 6. So that's term number 6. Which terms could you eliminate for a steady flow in a pipe aligned with the z-axis and open to atmosphere at both ends? So here's a pipe. It's open to atmosphere at both ends. It's got stuff flowing through it. And it's steady. Open to atmosphere at both ends. So if it's steady, I'm going to eliminate that one. If it's open to atmosphere at both ends, then I don't think there's any pressure gradient in the z direction. So no pressure difference as we move in the z direction. What other terms could we eliminate? Steady flow in a pipe aligned with the z-axis and open to the atmosphere at both ends. We don't know yet if it's fully developed. It might not be fully developed flow. So definitely we can eliminate term 1, but we can also eliminate term 5. So it's not only term 1. None is not a good answer. Terms 1 through 4, because there's no acceleration in the fluid. Well, again, if it wasn't fully developed, there could be some acceleration. So I think terms 1 and 5 are the ones we can eliminate. Question 5. 9 terms again, 4 on the left side, 5 on the right side. Which terms could we eliminate for flow over a wing with an extremely high Reynolds number? So there's our wing. The flow is coming very fast towards the wing. If the Reynolds number is really high, then if Reynolds number is large, then we're looking at the ratio of inertia to viscous forces. So if the inertial forces are way bigger than the viscous forces, we can probably eliminate the viscous terms and get a reasonably good approximation. Pressure gradient? No, there'll be pressure variations. The flow could be three-dimensional, so it's going to have changes in x, y, and z. And it might not be steady, so we can't eliminate that one. So I would say we can just eliminate these last ones. That was term 6, so 7, 8, and 9. That's the answer I would choose.